Did you know? When ChatGPT gives you an answer in just a tenth of a second, when AI creates a photorealistic image almost instantly, the real workhorse behind all this is not the CPU, the so-called brain of your computer. If you try to train the same AI model on a CPU, it might take a month. On a GPU, that same training could finish in a single day. Think about that 30 days versus 24 hours. So the natural question is, why can one GPU outperform dozens, sometimes even hundreds of CPUs? Why is the gap so huge? Today, let's peel back the layers and compare CPUs and GPUs. We'll look at their internal architecture, how they actually process data, and why GPUs are so perfectly suited for AI. Let's start with the CPU. CPU stands for Central Processing Unit. It's the part of a computer that coordinates almost everything, the operating system, applications, and the instructions that keep your machine running. A CPU is designed for flexibility. It can handle tasks that require decision-making, branching logic, and complex instruction sets. Think of it as a highly skilled engineer, capable of switching from one kind of problem to another in an instant. Most consumer CPUs today have between 4 and 16 cores. Server CPUs may have dozens, even hundreds. And each of these cores is powerful. It has branch predictors, schedulers, multi-level caches, and supports a wide range of instructions from simple arithmetic to encryption and compression. This makes the CPU excellent at running your operating system, managing files, browsing the web, and executing programs that require logic and variety. Now the GPU stands for Graphics Processing Unit. It was originally created for graphics rendering, pixels, polygons, textures, everything that goes into making a 3D game or an animated movie. But the way a GPU is built makes it fundamentally different from a CPU. Instead of a few strong cores, it has thousands, sometimes tens of thousands of smaller cores. These are called CUDA cores in NVIDIA's design, or stream processors in AMD's. Each of these cores is much simpler than a CPU core. They don't bother with heavy logic or complicated branching. Instead, they're optimized for raw arithmetic, adding, multiplying, and doing those operations again and again. And here's the key. Thanks to their SIMD design, a single instruction can command thousands of these little workers to perform the same calculation on different pieces of data, all at once. Think of it this way. A CPU is like a group of master chefs, each capable of cooking any dish, but only a few of them in the kitchen. A GPU is like an army of fast food cooks, each trained to make one burger, and when you need 10,000 burgers, nothing beats that. Let's make this more concrete with an example. Suppose we have 1,000 numbers, and we need to process them with these rules. If the number is even, add 1. If it's odd, multiply it by 2. If it's divisible by 7, replace it with 0. A CPU shines here. Its branch predictor guesses which condition comes up next. Its caches store the data. It can jump between if-else statements without breaking a sweat. Even with 1,000 numbers, it finishes in milliseconds. But the GPU, this kind of logic gives it trouble. Why? Because its cores must execute the same instruction at the same time. When you throw in multiple branches, odd, even, divisible by 7, some cores end up sitting idle while others do the work. This is called branch divergence, and it can drop efficiency to under 10%. In this case, the CPU is actually faster. But switch the task to matrix multiplication, and the story flips completely. Let's say we want to multiply 2 matrices, each 1024 by 1024. That's over 1 billion multiplications and additions. On a CPU, even with 16 cores working together, each core still handles tens of millions of operations. Plus, they need to constantly sync with one another. The whole process takes seconds. On a GPU, the job is split across thousands, even millions of tiny cores. Each processor handles just a handful of operations. Meanwhile, high bandwidth memory streams the data in without delay. The result? The same task that takes seconds on a CPU can finish in a tenth of a second on a GPU. This is why GPUs are the kings of AI computing. Think about AI workloads for a moment. Every neuron in a neural network does a dot product. Every layer requires a giant matrix multiplication. Convolutional networks slide filters across images, repeating the same calculation millions of times. This is not complex decision-making. This is repetitive, parallelizable math. And it's exactly the kind of work GPUs are designed to do. That's why in AI, parallelism isn't just a nice to have. It's essential. Let's take a real example. ResNet 50, a well-known deep learning model, needs tens of billions of operations just for one forward pass. Backpropagation, which trains the network, takes several times more. And over 90% of those operations are parallelizable. That's where GPUs like the NVIDIA H100 come in. This single GPU has more than 16,000 CUDA cores and special tensor cores just for matrix math. It can perform trillions of floating point operations per second. Here's how it plays out. A 1024 by 1024 matrix can be split into over 1 million subtasks, each handled by a different GPU core. A convolution sliding across an image. Each tiny patch of pixels can be assigned to a separate core. Activation functions. Every element in the array can be processed in parallel. It's like breaking a mountain of work into 1 million Lego blocks. and having a million hands put them together at once. Meanwhile, CPUs with a few dozen cores simply can't compete. But parallelism alone isn't enough. There's also the issue of feeding all these cores with data. AI models are massive. Training a trillion parameter model means moving gigabytes of data every second. If memory can't keep up, even the most powerful GPU cores just sit there idle. That's why GPUs use high bandwidth memory, or HBM. HBM3 can deliver more than 4 terabytes per second of bandwidth. That's 10 to 20 times more than DDR5 memory in CPUs. And GPU memory is also structured differently. It includes shared memory and caches optimized for parallel access, so thousands of cores can reuse the same data without waste. This ensures that when you unleash 100,000 cores on a problem, they all have something to do. No one is standing around waiting. Of course, hardware is only half the story. The other half is software. NVIDIA's CUDA platform is what makes GPU computing usable. It lets programmers break AI tasks into millions of threads and automatically maps them to GPU cores. Frameworks like TensorFlow and PyTorch take this further. When you write a neural network in Python, these frameworks silently call CUDA-optimized kernels behind the scenes. That's why with just a few lines of code, you can train a neural network on your GPU and it runs hundreds of times faster than on a CPU. It's the combination of three things, hardware, software, and the nature of AI tasks, that makes GPUs the heart of modern AI. Not coincidence, but inevitability. And the impact goes beyond AI. GPUs are accelerating progress in science, medicine, entertainment, and transportation. Climate researchers run models that used to take weeks, now in just hours. Biologists simulate protein folding hundreds of times faster, speeding up drug discovery. Animators render 4K special effects in seconds instead of hours, seeing results instantly. Doctors reconstruct CT scans in 10 seconds instead of 10 minutes. Genomic analysis that took days now takes hours. And in self-driving cars, GPUs process sensor data in under 100 milliseconds, fast enough to keep you safe. From exploring the universe, to curing disease, to powering the apps on your phone, GPUs are changing the speed and depth of human progress. This isn't just hardware evolution. This is parallel thinking applied to reality. Today, GPUs are no longer just graphics cards. They are the engines of the AI era. And that's it for today's video. If you enjoy deep dives like this, where computer science meets real-world technology, don't forget to like, subscribe, and hit the bell. Thanks for watching, and I'll see you next time.